I'm getting a couple of new scripts off of the eCampus repository. I'm getting WHAS100.R and that's enough, I think, for today. We looked earlier, I think, already at the ACTG320 file, and we'll look at that one again, too. Before we go to the data, wanted to go through a little bit more of the notes. Let me see if I can find them. Okay. So where were we? We were talking about the Cox proportional hazards model as a method for regression with survival data. So we started talking about this quantity called the hazard function, and it's defined as a density divided by survival probability. Maybe not the first thing you would think of and as the most obvious way to assess risk, but it has its, there's reasons for choosing this particular one. But the way that we interpret it roughly is as an instantaneous probability of failure at a particular time. Given that you have survived up to this time, how much risk is there at this particular instant? And it turns out that we can do regression with hazards in a reasonable way. The Cox proportional hazards model is that the hazard for a particular time with some covariates equals a baseline hazard function, which is a function of time, but not of the covariates, multiplied against e to the linear model piece. So something that depends on the covariates, but not on time. And remember that the coefficients of the proportional hazards model have these interpretations. A beta coefficient is a log hazard ratio. So e to the beta coefficient is a hazard ratio. Okay. Wanted to say just a couple of things about relating back and forth between a regression model and these survival curves. The survival curves are, kind of commonplace use, I guess, in bio applications, and so it's useful to be able to fit a regression model, but also say, estimate the survival curve for this set of covariates. Like, show me the estimated survival curve from our regression model for a male Caucasian in this particular group based on the regression model. So there is a relationship between hazard and survival curve. So we can go back and forth between, say, a Cox proportional hazards model and survival probabilities. In particular, the survival probability at time t is e to the minus capital H of t, where capital H is a cumulative hazard, just like capital F is a cumulative distribution function, an integral from the left up to a particular time of the PDF. Capital H is an integral from the left up to a particular time of the hazard. So it's like an accumulation of the hazards, those instantaneous risks, up to a given time. Survival probability equals e to the minus that. And from that, we can work our way back from a fitted regression model to an estimated survival curve. So if you do a Cox proportional hazards model, say, and you have a handful of covariates in there. And then you would like, as a summary picture, survival curve estimates for these 4 or 5 interesting comparison groups. Males in the control group, males in the treatment group, females in the control group, females in the treatment group, something like that. We can get estimated survival curves for arbitrary covariate choices. So I'll show you how to do that with at least one data set today. So I'm going to look at, first I wanted to go back to the serve script file. There was one little picture that I wanted to show that illustrates what a hazard is and how it relates to a PDF and a survival curve. So what is a hazard function? What does it look like? In this script, we've been simulating data that are censored and trying different things, showing how to estimate survival curves and how to use the Kaplan-Meier and that kind of thing. So here's another simulation where I'm going to say a sample of 100 events or event times. The mean is 5, standard deviation is 1.5, 30% of the individuals will be censored, and I'm going to generate the times from just a normal distribution. And then I am going to compute the density, so just the PDF of the event times, and the survival curve, capital S, of the event times, the actual survival curve, the thing that would start at 1 and go down to 0. And then we'll also look at the hazard just to see what does it look like. It's this instantaneous risk. It's a ratio of the PDF and the survival curve. So here is one illustration. Okay, so the green is the normal PDF. That is the distribution of event times. The survival curve is the 1 minus the CDF, and then the hazard is this kind of different thing that is rising as survival is decreasing. But it's not bounded at 1. But while the hazard is kind of an unusual thing to try to interpret, it is still intuitive in that it reflects, worse prognosis. Higher hazard values reflect worse prognosis. So let's go to the ACTG data real quick. These were AIDS patients in a clinical trial. 1,151 individuals, 16 variables, and we have event time, we have censoring indicator, and a bunch of covariates. Last time we looked at doing the Cox model with just the treatment variable. This, remember, has 2 treatment groups. It was like a 3-drug it was a 3-drug cocktail versus a 2-drug cocktail. And so we did one simple Cox model where we just had the treatment variable in there. So let's redo up to that point. I will go from here and look at the output of the fitted model again. Make this a little bit bigger. So we fit initially this Cox model where we said our event time is the response, model it in terms of this categorical binary variable for treatment. Remember that we said there was no intercept reported by the model, because the way that the proportional hazards model works, it factors out the baseline hazard function. So it's estimated as if there is no intercept. But this coefficient is a log hazard ratio. So if you exponentiate it, this is a hazard ratio estimate. We have a standard error, and so we can get a p-value for this variable. But let's consider some more models. Just FYI, let me go ahead and do this one as well. If you wanted a confidence interval for, say, the hazard ratio, that's the estimate right there, the estimated hazard ratio. If you wanted a confidence interval, what you can do is create, say, a 95% confidence interval for the original coefficient, because you have the standard error for that coefficient right here. You could do a confidence interval on beta, and then just exponentiate the endpoints of it to get a confidence interval for the hazard ratio. So that's what I'm doing right here. I'm taking beta hat plus or minus a 1.96 from the standard normal times the standard error of beta, and then exponentiating the thing. Okay, here's another model where we have, in addition to treatment, age and gender and CD4 and prior ZDV. Let me remind ourselves what CD4 and prior. So we have gender, we have CD4, which is baseline CD4 count, and prior use of the ZDV drug. Okay. So let's fit a model that, with sensor data, looks at treatment effect adjusted for age and gender and CD4 count and prior ZDV. So now we'll have usual multiple regression output. Now we have a coefficient for each of those covariates. These are then hazard ratios. We could get confidence intervals on the hazard ratios by exponentiating confidence intervals on the coefficients themselves. Okay. We can do tests with Cox models like we have done with the linear models. So we've seen likelihood ratio tests, we've seen those F-tests, we've seen walled style tests. They're in the Cox model setting, are likelihood ratio tests. So let me do a few slides real quick to get us to that point. But what we just said was there was a relationship between survival and a hazards model. So we can go back and forth between a Cox model and a survival curve. So let me show you how to do that survival curve before we move off of this picture. Estimated survival curve. So if I have a Cox model, fit 0 is a model that we're going to fit here, then you can use the serve fit function and pass in the covariates for the individual or the category that you want a survival curve for. So I'll return to this, I guess, when we get to this part of the script. But we'll have separate survival curves for two different categories. Okay. The way that we actually estimate a Cox proportional hazards model, it is not fully parametric, this would be the full likelihood for fitting the model that we've written down. It's a likelihood contribution for individuals that are uncensored, for which there was actual event time, raised to the delta. And then there's a survival contribution for those that were censored, raised to a 1 minus the delta. It's just like that likelihood that we had earlier on in the slides. But in order to fit this model, a fully likelihood model like this, that H at least requires a choice of a distribution. So like the normal distribution, I assume, for the survival times, or gamma or something. And what Cox wanted to do was avoid having to specify a distribution. And so he proposed a different likelihood target, not the likelihood that you would write down technically, but this other thing called the partial likelihood. It is just another way of expressing all the beta coefficients related to the observed data, and it needs to be maximized. So there are results that Cox pH function in R does for us to maximize that function with respect to beta, give us estimates like maximum likelihood estimates, but these are more maximum partial likelihood estimates. We can also get standard errors for the coefficients, and in fact all the covariances between the coefficients as well, like a full variance covariance matrix for the betas, using what's like maximum likelihood theory. So I'll let you look at that if you're interested. If you have seen the idea of information matrix, Fisher's information matrix, if you're familiar with its role in maximum likelihood estimation, it shows up here. And then I just worked out, if you've never seen that before, when we wrote regression models as a y equal x beta kind of representation earlier on in the course, we ended up saying a few things. One was that the estimate of beta, the least squares, which is also the maximum likelihood under the normal model, estimate is written this way: x transpose x inverse, x transpose y. And the variance is this form: sigma squared x transpose x inverse. And under the normal model, the information matrix that I referenced on the previous slide is the variance covariance matrix for the betas that we saw earlier on in the course. So if you're interested in where the connection is and what the role is played with the Fisher information matrix, you might look at that slide a little bit more. Because we are working with a likelihood-like quantity in estimating the models, we're working with this partial likelihood, there are results that are like likelihood ratio tests that we can use here. So we can test hypotheses about the beta coefficients, like is beta 2 equal to 0, or are these two beta coefficients the same, or do these two beta coefficients sum to 0, or anything like that. We can test using partial likelihood ratio tests. So I'll show you how you can get the likelihoods from our fitted models, and then you can test anything that you want. There's also walled-like tests, which is what we've been using with beta coefficients with regression. Estimate minus the null value that you're hypothesizing, divided by the standard error of the estimate. And here, those, at least with a decent sample size, can be assumed to be normal 0, 1 under the null. Okay, I'll leave this for later, but we are going to want to think, when we're doing Cox proportional hazards, about whether the assumptions that it makes are reasonable, because it does make a kind of big assumption. The proportional hazards assumption is a big assumption. It's nice because it allows us to not have to specify a distribution, but it needs to be checked. We'll get to that next time. Okay, so let's come back to the ACTG data and play with our new toys a little bit here. We just fit this model a moment ago with treatment, age, gender, CD4 prior. Suppose we wanted to test whether all 5 of the coefficients were equal to 0. As in, there's no structure with respect to these 5 predictor variables at all. A likelihood ratio test, like we've seen before, looks like fit an unrestricted model, and with respect to whatever null hypothesis you have in mind, fit the model where that's true, where that null hypothesis is true. So you have 2 models, an unrestricted and a restricted model, and then we have a -2 times a log likelihood ratio. We saw that earlier on in the course, likelihood ratio tests. From the fitted objects of Cox pH, we can get log likelihoods that correspond to the model. So this will, let me fit these 2 models. We're going to compare the one with all 5 covariates in it to the one that has nothing in it. So each of these fitted objects, like names fit, each of these have, among other things, a log likelihood element. So fit $log like. So this is actually going to be, I think, both the log likelihood for the fitted model and the null model. I think it has them both in there already. Fit $0 log like. Yeah, I think this is the log likelihood for the unrestricted model, and that is the log likelihood for everything's been taken out. So I'm going to do this is the null log likelihood, and the second element of that first one is the unrestricted log likelihood. So this capital G is a likelihood ratio statistic, -2 times the log likelihood ratio, or -2 times the difference of the log likelihood ratios, or -2 times the log of the difference of the logs. Okay, and then p-value then is, like we've done before with likelihood ratios, we compare that -2 times the log likelihood ratio to a chi-square with degrees of freedom equal to the number of coefficients that have been pulled out of the model. In this case, that would be 5, because we started with 5 covariates, compared it to the model with none, and p-value is probably 0, essentially, yeah. So that's an illustration of doing likelihood ratio tests. I've got a couple more down here. Suppose we wanted to test whether only the coefficients for gender and prior ZDV equals 0. So we're going to compare back to this full model again with all 5 of the covariates and consider the null model as not having those 2 covariates in it. So it's everything except those 2. is now fit 0. So this is the same idea. Fit up above is the unrestricted model. Now we have a different restricted model. The degrees of freedom between these two is now 2, because we're only taking 2 out. That p-value that we computed originally for taking all the variables out, comparing to the very null model with no covariates in it, would actually be reported in the Cox pH output, but this one would not be. So it's handy to be able to do a likelihood ratio test if you have your own specific test that you want to do, as opposed to just, is everything null versus no. Like here, if we wanted to ask specifically, can gender and prior be removed from the model? You can use likelihood ratio tests. Okay, let's see. Here is getting an estimated survival function for a specific category. For example, how about a treated individual, 38 years old, 74.5 cells per milliliter of CD4. And let's also get a survival curve for an untreated individual, same age and CD4. Based on a model that incorporates all the covariates that we think are relevant, here are our best survival curve estimates. These data are kind of interesting because there are very few events. Names, data, table. How many of the times were actual events? Only 96 of them. So almost all of the individuals were right-censored. So we have survival curve estimates that never have enough events to push them down below 0.9. Here's another model or way to fit a model to these data, which is just kind of a good exercise. Let's consider survival time versus a single continuous covariate, CD4 count in this case. So the coefficient of a Cox model is a log hazard ratio. That should be ratio. A beta coefficient is a log hazard ratio associated with usual slope type interpretation language, associated with a 1 unit increase in CD4 count. The range of CD4 here goes from like 0 to almost 400. So arguably it's not all that interesting to express something to a clinician about this is what we think happens for every 1 unit increase of CD4. I would never consider one person versus another in terms of one difference in CD4, say. So it'd be more useful for descriptive purposes if we would maybe change the scale to make the interpretation of the coefficient more maybe clinically relevant. For these CD4 data, the 3 quartiles were these things. Standard deviation was 70, and one of our books that was mentioned in the syllabus recommended using 1/2 the interquartile range, or 1 SD, as the target transformation. So a 1 standard deviation increase based change in terms of a hazard ratio would be e to the beta coefficient times 70, because the standard deviation was 70. So anyway, there's ways to translate the model into more interpretable estimates. Confidence intervals you can get by, again, exponentiating confidence intervals on a coefficient. Okay. If you wanted, for example, 70 times the beta coefficient, 70 times the beta coefficient was the log hazard ratio associated with a 1 standard deviation increase in CD4. So suppose we wanted that estimate, but we also wanted a confidence interval. We could get a confidence interval on the 70 times the beta and then exponentiate it. Okay, let's also look at the WHAS 100 data. I don't think we've seen these yet. Yeah, I have some more survival curve stuff in here. So these come from a heart attack study. We have 100 individuals, 9 variables. We have follow-up time, length of follow-up or follow-up time is the event time, and follow-up status is the censoring indicator. Age, gender, and BMI. Let's look at the survival curves for these individuals. We have 100 individuals. How about we look at the first few rows of head data. Censoring indicator. What is the difference between time and censor and time D and censor D? This doesn't have any mention of that. Oh, okay. So it did not find that file. Okay, sorry. I need to get that file. So data. Okay, now let's look at the data. Yeah, so they have different representations of dates, which we would have to process to be able to get into usable format, which we could do, but we don't have to because we have the length of follow-up, the actual time, in a separate column. And then this is the censoring indicator. Okay, so let's look at the overall survival curve for these individuals. time, let's see, these are days. Follow-up time in days on the horizontal axis, and then survival probabilities that are estimated Kaplan-Meier style on the y-axis. So there's a pretty significant decline in the survival probabilities over the first year or so, and then it levels out and is very highly variable at the very end. So it looks like most of the action happened quickly in the first year among this population. To get percentiles of survival probabilities, so what's the median survival time? It's the 25th percentile, or we can look at the output from SurvFit, and the survival column, wherever it drops below the target percentile, that's the time that we grab as the estimate. We've already seen how to do this. If you have a Kaplan-Meier curve and want to estimate the mean survival time, you can integrate it, so to speak. This has another example of the log rank test, with here testing survival curve equality between genders. Let's look at what those look like. So here are survival curve estimates for males compared to those for females. And this is another obvious case where it's going to clearly reject the null hypothesis because they are clearly different. Although that's not as small as I might expect. Fit 0. Yeah, that's the right picture. There must just be a fair amount of uncertainty around these estimates for the p-value to be that not tiny. Okay. So I have code here for estimating a survival curve on the basis of a fitted model, but I don't think we need to go through that because you already know how to get a survival curve from the ACTG data. We had survival curve like this, SurvFit on a fitted object. I think that's the easiest way to get an estimated survival curve. This is really just illustration of what is going on behind the scenes that I've shown in previous semesters, but I'm not sure we need to go through it. Okay. All right, I think that's enough of that. So is everybody moving to Canada? Yeah, I heard about that. Let's see. So I do need to address the proportional hazards assumption for Cox models. Got several examples of using Cox models. They're easy to do and relatively easy to interpret, but the big drawback is the assumption that you have to make that there's this proportionality, that hazard is a function of time but not covariates. Covariates do not depend on time, or the effects of covariates don't depend on time. So what we're going to do is create a picture that is kind of a diagnostic for whether this assumption looks reasonable. So I'll show you a picture in a minute, but we're going to say that the log of the minus log of a survival curve is equal to the log of a cumulative hazard function plus a beta coefficient. And the log of the survival curve for a comparison group is the same thing except not beta. Long story short, if the Cox proportional hazards model holds, then this is one way that we should be able to highlight that it holds. If we fit two survival curves, like in this case, one for a treatment group, one for a control group, we fit two of them and log minus log transform them, they should roughly be separated by a constant amount, parallel to each other. So let's look at an example of that. I'll just show you what one looks like, and then we can go back and look at the slides maybe next time. With one of our data sets, at least, I know I have code for checking the assumptions of proportional hazards. I don't think it's in this one. And it wasn't in this one, I don't think. I'll show you what it looks like next time then. So let's come back here and just think about what we're going to do. The assumption, the proportional hazards assumption, is that the hazard at a time t with covariance x can be factored into baseline hazard at time t and something e to the x beta. So the key thing is that the effect of the covariate does not change with time. And because of the relationship that we saw earlier between a survival probability and a cumulative hazard, if you just apply a log transform and then negative that and then log transform again, you have this relationship that I was describing. So if you have a binary covariate like treatment and control, and you want to ask, does proportional hazards appear to hold with respect to that covariate? That's really what we want to do with a Cox model, is ask, does proportional hazards appear to hold with respect to each of the covariates in the model? So for this covariate, we can get an estimated survival probability curve for treatment group and one for control group, and they need to be approximately linear or parallel to each other. So I'll show you how to do that next time. But I don't know which data set I have with the code in it, so I won't waste your time while I look for that. But it does get more complicated. So if we just have one binary covariate like treatment and control, it's easy to do this rough diagnostic check. But it does get more complicated when you have more than two comparison groups or when you have multiple covariates in the model, because technically you need to check whether the, quote, proportional hazards assumption holds for each of the covariates in your model. So good news is that there are some functions in R that will give us a p-value for checking that assumption. So does it look like proportional hazards holds for each of the variables? But it's also good to be able to look at it, and this type of picture helps you to at least try to look at it. Yeah, I'll show you this function. This function will actually test, does proportional hazards hold for this data? It gives us a p-value for each of the covariates in the model, and then it puts those together somehow into an overall p-value for does proportional hazards appear to hold for this model. Okay, I think we'll quit there. And next time I want to show you that WHAS 500 script, because I'm referring to it in the homework. The last two problems in the homework, I'm asking you to go through a kind of step-by-step model building process. I don't agree with all of the steps that they take necessarily, but I think it is a good way to, from the ground up, assess what the data look like and what reasonable choices for a model would be. So we'll go through that one on Friday. That way you'll be able to work on this. Okay, thank you. See you Friday.